Right now, at this very moment, 500 million miles away, a storm larger than Earth has been raging for centuries. It's a tempest so vast and enduring that it has become as iconic as the planet it inhabits. Everything we thought we knew about weather, about storms, about the very nature of atmospheric fury, must be reconsidered when we gaze upon this cosmic maelstrom. Welcome to Sleep About Science. Tonight we're exploring Jupiter's Great Red Spot through 100 remarkable facts that will take us on a journey from ancient observations to cutting-edge discoveries. And if you drift off to sleep while listening, that's perfectly wonderful. In fact, there's something rather poetic about falling asleep while contemplating a storm that itself has been a kind of cosmic slumber, persistent, enduring, and beautifully unchanging across the centuries. Before we begin, please make yourself comfortable, wherever you are in the world right now. Whether it's late evening in London, the quiet hours of night in Tokyo, or perhaps you're listening during a peaceful afternoon in Sao Paulo, Mies. Allow yourself to settle in, pull your blankets up, adjust your pillow, and let yourself sink into whatever comfortable position brings you peace. And remember, this is educational content for your curious mind to explore. But there's no test at the end, no pressure to remember every detail. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into science that help us understand our remarkable universe. Now, let's begin our exploration of one of the most extraordinary phenomena in our solar system, where we'll discover that this great red spot isn't just a storm wind, it's a window into the alien physics of gas giant worlds, a testament to the power of fluid dynamics on planetary scales, and perhaps most remarkably, a storm that has been watching over Jupiter longer than humans have been studying the stars. It's a cosmic lighthouse that has guided astronomers' eyes for generations, a faithful companion to Jupiter that has outlasted civilizations and witnessed the entire development of modern astronomy. Picture, if you will, standing on the surface of Jupiter Myrter, though of course there is no surface in the way we understand it. Jupiter is a world of endless atmosphere, clouds stacked upon clouds, with layers of gas extending down for thousands of miles until pressure and temperature become so extreme that hydrogen itself transforms into something metallic and strange. But imagine hovering somehow in this alien sky, surrounded by the swirling, turbulent atmosphere of the largest planet in our solar system. Above you, below you, around you, in every direction stretches an ocean of gas, an atmosphere so deep and complex that our entire Earth could be swallowed within it and barely create a ripple. The Great Red Spot is fundamentally an anticyclonic storm, meaning it rotates in the opposite direction to Jupiter's rotation. While hurricanes on Earth are cyclonic storms that rotate with our planet's spin, Jupiter's Great Red Spot spins against the grain, creating a high-pressure system that rises above the surrounding cloud layers like a massive atmospheric mountain. Imagine standing atop a mountain peak on Earth and looking down at the landscape below. This is similar to how the Great Red Spot looms above Jupiter's cloud deck, elevated and prominent, a towering edifice made not of rock and stone but of swirling gases and complex chemistry. This storm is truly ancient by any earthly measure, a cosmic grandfather clock that has been ticking away the centuries with its steady rotation. The first confirmed observations date back to 1831, when astronomers with increasingly sophisticated telescopes began to systematically map and study Jupiter's atmospheric features. But there are sketches and descriptions from as early as 1665 that may depict the same phenomenon. Observations made by Giovanni Cassini, the same astronomer who discovered several of Saturn's moons and made groundbreaking observations of Jupiter's atmospheric bands. Think about that for a moment, and let the enormity of this timeline wash over you. This storm may have been raging when Isaac Newton was developing his laws of motion, when Shakespeare's plays were still fresh in memory, when the printing press was revolutionizing human knowledge, while human civilizations rose and fell, while technologies advanced from simple telescopes to space probes, while we learned to fly and eventually to leave our planet entirely, this storm has continued its ancient dance in the Jovian sky, unchanged in its essential character, even as empires crumbled and new nations were born. The sheer size of the Great Red Spot defies easy comprehension, challenging our earthbound sense of scale in ways that can be both humbling and awe-inspiring. At its largest recorded dimensions, it measured roughly 25,000 miles across and 12,000 miles tall. To put this in perspective that might help your mind grasp the enormity, you could fit 2 to 3 Earths side by side within its boundaries. Imagine looking down from space and seeing a storm that could swallow our entire planet whole, and you begin to grasp the scale we're dealing with. Picture every hurricane, every typhoon, every tornado that has ever existed on Earth, and realize that they would all be mere specks compared to this single atmospheric feature on Jupiter. But here's something that might surprise you. Something that adds an element of mystery to this already enigmatic storm of the Great Red Spot has been shrinking. When Giovanni Cassini first observed it in the 1600s, it may have been even larger than those 19th century measurements suggest, possibly spanning distances that could accommodate 4 or even 5 Earths. By the late 1800s, when systematic observations became more regular and precise, it was about 25,000 miles wide. Today, it's roughly 10,000 miles across, still enormous by any earthly standard, still larger than our entire planet, but notably smaller than its historical dimensions. This shrinkage raises fascinating questions about the storm's life cycle and ultimate fate. Is this a natural evolution, a slow transformation that's part of some cosmic cycle we don't yet understand? Or could it be responding to changes in Jupiter's atmospheric conditions, perhaps variations in the planet's internal heat output, or modifications in the global circulation patterns that help sustain it? Scientists continue to study this phenomenon, using both historical observations and modern spacecraft data to understand what drives these changes and what they might tell us about the future of this remarkable storm. The color that gives this storm its name comes from complex chemical reactions in Jupiter's atmosphere, a cosmic paint palette created by conditions that exist nowhere else in our solar system. Scientists believe the red hue results from phosphorus compounds, sulfur, or organic molecules called chromophores being lifted from deeper atmospheric layers and then altered by solar ultraviolet radiation. It's essentially cosmic chemistry happening on a planetary scale, painting this massive storm in shades of brick red, salmon, and sometimes even brown, colors that shift and change as different chemical compounds rise and fall within the storm's circulation. Imagine, if you will, the delicate chemistry happening within this tempest. Deep below the visible cloud tops, in layers where pressure is many times greater than anything on Earth's surface, complex molecules are being forged and transformed by the storm's circulation. These substances are carried upward by the storm's powerful convection, rising through layers of ammonia ice, water vapor, and hydrogen sulfide, until they reach altitudes where solar radiation can work its transformative magic. The ultraviolet light from the sun, that same radiation that gives us sunburns and creates the northern lights in our own atmosphere, strikes these molecules and changes their structure, their properties, their very identity, creating the compounds that give the Great Red Spot its distinctive appearance. The winds within the Great Red Spot reach truly staggering velocities that put even our most extreme earthly weather to shame. At the storm's edge, wind speeds can exceed 250 miles per hour, faster than the strongest hurricanes ever recorded on Earth, faster than the jet streams that commercial aircraft ride to cross our continents. These winds maintain their fury year after year, decade after decade, powered by Jupiter's internal heat and the planet's rapid rotation. Picture standing in winds that could lift buildings, that could turn any earthly structure into debris, and realize that these winds have been blowing continuously for longer than human civilization has existed. Speaking of rotation, Jupiter spins remarkably fast for such a massive world, a cosmic paradox that seems to defy our intuitive understanding of how large objects should behave. A day on Jupiter lasts only about 10 hours, meaning this gas giant completes one full rotation in less time than it takes most of us to sleep. This rapid spin creates powerful Coriolis effects, the same force that influences weather patterns on Earth but amplified to extraordinary proportions, that help maintain and structure storms like the Great Red Spot. The Coriolis effect on Jupiter is so strong that it fundamentally shapes the entire atmospheric circulation of the planet. Picture the way water spirals down a drain, but imagine that effect scaled up to planetary proportions and maintained by forces so powerful they could reshape continents if applied to our world. This rotation creates the banded structure that makes Jupiter so recognizable in photographs. Those alternating light and dark stripes that circle the planet like cosmic racing stripes are actually massive jet streams, rivers of wind that flow around the planet at different latitudes and different speeds. The storm sits in Jupiter's southern hemisphere, specifically in the South Tropical Zone, at approximately 22 degrees south latitude. It's locked into this position by the jet streams that flow like rivers of wind around Jupiter's atmosphere, creating what scientists call a solitary wave, a stable atmospheric feature that can persist indefinitely under the right conditions. Think of it like a massive boulder in a rapidly flowing river, creating a stable eddy downstream that maintains its position despite the powerful currents flowing around it. This positioning is crucial to understanding why the Great Red Spot has persisted for so long. On Earth, our weather systems are constantly being disrupted by the interaction between land and sea, by mountain ranges that force air masses up and over barriers, by the complex geography that makes our planet's surface so varied and interesting. But Jupiter has no such complications. It's a world of endless atmosphere, layer upon layer of gas extending down into the planet's mysterious interior. What makes the Great Red Spot so stable compared to Earth's storms is Jupiter's lack of land masses, a fundamental difference that creates an entirely alien meteorology. On our planet, hurricanes weaken rapidly when they move over land because they lose their energy source, the warm, moist air rising from tropical oceans, and encounter friction from forests, mountains, and urban landscapes. Jupiter's Great Red Spot exists in a world of endless atmosphere, with no continents to disrupt its flow, no ocean boundaries to constrain its movement, allowing it to maintain its structure for centuries like a cosmic gyroscope spinning in the vacuum of space. The depth of the Great Red Spot has been one of its greatest mysteries, a question that has puzzled scientists for generations and only recently begun to yield its secrets. Recent data from NASA's Juno mission, which has been orbiting Jupiter since 2016 like an artificial moon dedicated to unraveling the planet's mysteries, suggests that the storm extends roughly 200 miles deep into the atmosphere. That's about 25 times deeper than Earth's deepest storms, yet still represents only a small fraction of Jupiter's total atmospheric depth, which may extend thousands of miles down before reaching whatever solid core might exist at the planet's heart. To put this depth in perspective, imagine diving into Earth's deepest ocean trenches and continuing down another 100 miles beyond the seafloor. The pressures at the bottom of the Great Red Spot are crushing by earthly standards, yet still represent only the upper portions of Jupiter's atmospheric ocean. This gives you some sense of the incredible scale we're dealing with. NICEA's storm system, that would be unimaginably deep by our standards, is actually a relatively shallow feature on Jupiter. Jupiter's atmosphere is primarily composed of hydrogen and helium, the simplest and most abundant elements in the universe, the same materials that fuel the nuclear fires of stars. But mixed within this cosmic cocktail are traces of methane, ammonia, hydrogen sulfide, and water vapor, compounds that create distinct cloud layers at different altitudes and temperatures. The Great Red Spot draws material up from these deeper layers through its powerful circulation, creating its complex chemistry and distinctive coloration, like a cosmic mixer blending ingredients from different levels of Jupiter's atmospheric cake. The layered structure of Jupiter's atmosphere is something like a vast three-dimensional ocean with different properties at different depths. Near the top, where space begins and atmosphere ends, temperatures are frigid, hundreds of degrees below zero. But as you descend into the atmospheric depths, pressure and temperature both increase dramatically. Deep within Jupiter's atmosphere, conditions become so extreme that hydrogen, normally the lightest and simplest of gases, begins to behave like a metal, conducting electricity and creating magnetic fields that contribute to Jupiter's powerful magnetosphere. The temperature at the top of the Great Red Spot is actually quite cold by earthly standards, around minus 200 degrees Fahrenheit, cold enough to freeze air itself if air could exist at those pressures. But remember, this is Jupiter, where the internal heat from the planet's formation billions of years ago still contributes significantly to atmospheric dynamics. Jupiter actually radiates more energy into space than it receives from the Sun, like a cosmic furnace slowly cooling but still warm from its violent birth in the early solar system. This internal heat source is crucial to understanding why Jupiter's weather is so dramatically different from Earth's. Our planet's weather is primarily driven by solar heating. The Sun warms the equator more than the poles, creates temperature differences that drive wind patterns, powers the water cycle that brings us rain and snow. Jupiter's weather, by contrast, is powered from within, driven by heat that has been trapped inside the planet since the solar system was young. This internal energy source helps explain why storms like the Great Red Spot can persist for centuries, drawing on an energy supply that dwarfs anything available to earthly weather systems. One of the most remarkable aspects of the Great Red Spot is its longevity in a chaotic system, its ability to maintain its identity and structure in an environment that should, by all rights, tear it apart. Jupiter's atmosphere is incredibly turbulent, with multiple jet streams flowing at different speeds and directions, smaller storms constantly forming and dissipating, and complex weather patterns that interact in ways we're only beginning to understand. Yet the Great Red Spot has persisted through all this chaos, like a massive atmospheric gyroscope maintaining its position and structure, despite being buffeted by forces that could reshape continents. This persistence in chaos is one of the most fascinating aspects of the Great Red Spot from a scientific perspective. In fluid dynamics, the branch of physics that studies how liquids and gases move. We know that turbulent systems tend to break down organized structures over time. Eddies and vortices in turbulent flows typically dissipate their energy and disappear relatively quickly. The fact that the Great Red Spot has maintained its coherent structure for centuries suggests that it has found a kind of stable equilibrium, a balance point where the forces trying to tear it apart are exactly matched by the mechanisms that maintain its integrity. The storm has been observed to interact with other atmospheric features on Jupiter in ways that demonstrate both its power and its complex relationship with the broader Jovian atmosphere. Sometimes smaller storms merge with the Great Red Spot, temporarily changing its appearance or intensity, like cosmic fuel being added to an already massive fire. These merger events can be quite dramatic when observed through telescopes, with the smaller storm being stretched and distorted as it's absorbed into the larger system, its material and energy becoming part of the Great Red Spot's ongoing circulation. Other times, the Great Red Spot deflects or absorbs nearby weather systems, demonstrating the immense influence it has on Jupiter's broader atmospheric circulation. Picture a massive ship moving through the ocean, creating waves and currents that affect smaller vessels for miles around. The Great Red Spot has a similar effect on Jupiter's atmosphere, influencing weather patterns and atmospheric flows across vast distances, creating ripples in the atmospheric ocean that can be detected far from the storm itself. From Earth, the Great Red Spot appears as a reddish oval that transits across Jupiter's disk as the planet rotates, a cosmic lighthouse that sweeps past our view every 10 hours or so. Amateur astronomers with modest telescopes can observe this feature, making it one of the most accessible examples of extraterrestrial weather for backyard stargazers. The fact that we can see individual storm systems on another world with relatively simple equipment is truly remarkable when you think about it. With a telescope costing less than a computer, you can observe weather patterns on a planet hundreds of millions of miles away. This accessibility has made the Great Red Spot one of the most studied features in the solar system, observed by countless amateur and professional astronomers over the centuries. Each observation adds to our understanding, creating a database of atmospheric behavior that spans human lifetimes and allows us to study how planetary weather systems evolve over timescales impossible to observe on Earth. The Great Red Spot's apparent motion across Jupiter's surface occurs because the storm rotates at a different speed than Jupiter's magnetic field, creating a kind of cosmic drift that has been measured and tracked for decades. While Jupiter's magnetic field rotates once every 9 hours and 55 minutes, what we consider the planet's official rotation period, the Great Red Spot takes slightly longer to complete one circuit, causing it to drift slowly relative to other atmospheric features like a cosmic wanderer following its own schedule. This differential rotation reveals something important about the relationship between Jupiter's magnetic field, generated deep in the planet's metallic hydrogen core, and its atmospheric circulation, which occurs in the outer layers of gas that we can observe. The fact that these two systems rotate at slightly different rates tells us that Jupiter's atmosphere has some independence from the deeper planetary structure, that it's not simply locked in rigid rotation with the planet's interior. This storm system generates its own magnetic signature that can be detected by sensitive instruments aboard spacecraft that venture into Jupiter's vicinity. As the charged particles within Jupiter's magnetosphere interact with the Great Red Spot's complex electrical fields, they create subtle variations in the local magnetic environment that spacecraft can measure and analyze. These magnetic signatures provide another way to study the storm's internal structure and behavior, offering insights that complement the visual observations made with cameras and telescopes. The magnetosphere of Jupiter is itself a wonder that dwarfs anything in our earthly experience. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, creating a vast region of trapped charged particles that extends millions of miles from the planet. If this magnetosphere were visible to the naked eye, it would appear larger than the full moon as seen from Earth, despite Jupiter's enormous distance from our world. The Great Red Spot experiences what scientists call flaking events, where chunks of material break away from the storm's edges like cosmic icebergs carving from a glacier. These events were first noticed in detail during recent years of high-resolution observation, particularly through images from the Hubble Space Telescope and various Jupiter-orbiting spacecraft. They provide insights into how the storm maintains its boundaries and how material circulates within Jupiter's atmosphere, revealing the dynamic nature of what might otherwise appear to be a static feature. These flaking events are particularly fascinating because they show us that the Great Red Spot, despite its apparent stability, is actually a dynamic system in constant flux. Material is continuously being exchanged between the storm's interior and the surrounding atmosphere, with pieces breaking away and new material being incorporated in an ongoing dance of atmospheric circulation that maintains the storm's overall structure while constantly renewing its substance. The storm's oval shape is not perfectly stable. It oscillates slightly, sometimes appearing more elongated, other times more circular. These shape variations follow patterns that scientists are still working to understand, but they appear to be related to interactions with Jupiter's jet streams and the internal dynamics of the storm itself. Picture a balloon being gently squeezed and released in a rhythmic pattern, and you begin to get a sense of how the Great Red Spot's shape responds to the various forces acting upon it. These oscillations occur over timescales ranging from months to years, suggesting that they're driven by long-term variations in Jupiter's atmospheric circulation rather than short-term weather events. By studying these shape changes, scientists can learn about the forces that influence the storm and the mechanisms that help maintain its stability over such long periods. Recent computer models suggest that the Great Red Spot may actually be a relatively shallow feature compared to Jupiter's total atmospheric depth, more like a vast surface storm than a deep atmospheric phenomenon. While 200 miles might seem incredibly deep by earthly standards, Jupiter's atmosphere extends thousands of miles down before reaching the planet's presumed solid core, making the Great Red Spot more like a feature on the surface of an atmospheric ocean than a disturbance that extends to the very depths of the planet. This shallow nature has important implications for understanding how the storm maintains itself and interacts with Jupiter's broader atmospheric circulation. If the Great Red Spot were a deep phenomenon extending far into Jupiter's interior, it might be much more stable and resistant to change. As a relatively shallow feature, it must constantly interact with and adapt to changes in the upper atmospheric layers, making its persistence over centuries all the more remarkable. The storm rotates completely once every 6 to 7 Earth days, a rotation rate that has remained remarkably consistent over the decades of observation. This consistency suggests that whatever mechanisms drive and maintain the Great Red Spot are incredibly stable and self-regulating, operating like a cosmic clock that keeps accurate time despite the chaotic environment in which it exists. The rotation of the Great Red Spot is not uniformity. Different parts of the storm rotate at slightly different speeds, creating internal circulation patterns that are incredibly complex and beautiful when revealed through high-resolution imaging. The center of the storm rotates more slowly than the edges, creating a kind of differential rotation that generates shear forces and internal structure within the system. Lightning has been detected within the Great Red Spot, though not as frequently as in some other regions of Jupiter's atmosphere. When lightning does occur within this cosmic tempest, it's likely thousands of times more powerful than lightning on Earth, creating brilliant flashes that can be detected from space by sensitive instruments. These lightning strikes provide insights into the electrical processes occurring within the storm and the complex interactions between different types of particles and energy within Jupiter's atmosphere. The lightning in Jupiter's atmosphere is fundamentally similar to lightning on Earth. It's caused by the buildup and discharge of electrical charge within storm systems. But the scale and power of Jovian lightning reflects the extreme conditions in Jupiter's atmosphere, where pressures, temperatures, and energy densities far exceed anything in our earthly experience. The Great Red Spot influences weather patterns across a significant portion of Jupiter's southern hemisphere, demonstrating how a single atmospheric feature can affect climate on a planetary scale. Its gravitational and atmospheric effects create ripples in the flow patterns that extend far beyond the storm's visible boundaries, influencing the formation and movement of other atmospheric features across vast distances. This planetary scale influence is something that has no real analogue in Earth's weather systems. While large storms on our planet can certainly affect weather patterns across continents, nothing in our experience compares to the way the Great Red Spot shapes atmospheric circulation across an entire hemisphere of a planet larger than all the other planets in our solar system combined. The storm's color has varied over the years of observation, sometimes appearing as a deep brick red, other times more salmon-colored or brownish. These color changes likely reflect variations in the chemical composition of material being lifted from different atmospheric depths, or changes in the intensity of solar radiation affecting the storm. The color variations provide clues about the internal dynamics of the storm and the complex chemistry occurring within Jupiter's atmosphere. These color changes are subtle but measurable, tracked by astronomers who have maintained detailed records of the Great Red Spot's appearance over many decades. By comparing these observations with our understanding of atmospheric chemistry, Scientists can infer what types of chemical processes might be responsible for the different hues and how these processes might vary over time. Scientists have calculated that the energy contained within the Great Red Spot is equivalent to hundreds of Earth's most powerful hurricanes combined, a concentration of atmospheric energy that staggers the imagination. This energy is maintained by Jupiter's internal heat source. Nice, the planet still radiates more energy into space than it receives from the Sun, a leftover from its formation 4.6 billion years ago, when gravitational collapse heated the planet's interior to temperatures that still persist today. To put this energy in perspective, consider that the most powerful hurricane ever recorded on Earth released energy equivalent to several hundred nuclear weapons. The Great Red Spot contains the energy of hundreds of such storms, all concentrated in a single atmospheric feature that has been maintaining this enormous energy content for centuries. It's a natural powerhouse operating on scales that dwarf any earthly phenomenon. The pressure at the center of the Great Red Spot is higher than the surrounding atmosphere, creating what meteorologists call a high-pressure system. This is actually opposite to most storms on Earth, which are typically low-pressure systems where air rushes inward toward the center of lower pressure. The high pressure in the Great Red Spot helps explain why the storm appears elevated above the surrounding cloud layers, like an atmospheric mountain rising above the Jovian landscape. This high-pressure nature is one of the key factors that makes the Great Red Spot so different from terrestrial storms. On Earth, storms are typically driven by air rushing inward toward areas of low pressure, creating the spiral patterns we see in hurricanes and typhoons. The Great Red Spot's high-pressure nature means that air flows outward from its center, creating a very different type of circulation pattern that contributes to its stability and longevity. The Great Red Spot has been used as a natural laboratory for studying fluid dynamics under extreme conditions, providing insights that apply to many other systems throughout the universe. The physics governing its behavior, the interaction of rotation, pressure gradients, and thermal convection, apply to everything from ocean currents on Earth to the circulation patterns in stellar atmospheres to the formation of spiral galaxies. This makes the Great Red Spot far more than just an interesting weather phenomenon. It's a cosmic laboratory where we can study fundamental physics under conditions that cannot be replicated in any earthly laboratory. The insights gained from studying this storm have contributed to our understanding of fluid dynamics, atmospheric science, and even astrophysics. Observations of the Great Red Spot have revealed the presence of complex vertical structure within the storm, showing that it's far from a simple, uniform rotating system. Rather than being a straightforward vortex, it contains multiple layers of circulation, with different parts of the storm moving at different speeds and in slightly different directions. This vertical structure creates a three-dimensional complexity that challenges our understanding of how such systems maintain their coherence over long periods. Recent high-resolution imaging has revealed that the storm has internal structure resembling a kind of atmospheric architecture, with different circulation cells at different altitudes interacting in complex ways. This structure is constantly evolving and changing, yet somehow maintains the overall identity and characteristics that make the Great Red Spot recognizable across centuries of observation. The storm appears to derive some of its energy from smaller storms that it occasionally absorbs, like a cosmic predator feeding on smaller atmospheric prey. When these merger events occur, they can temporarily brighten the Great Red Spot's color and increase its rotation speed, adding fuel to an already massive atmospheric fire. These interactions provide insights into how energy and material are exchanged between different scales of atmospheric motion on Jupiter. The merger events are particularly dramatic when observed through high-resolution telescopes or spacecraft cameras. Smaller storms approaching the Great Red Spot are stretched and distorted by the larger system's powerful circulation, eventually being torn apart and incorporated into the main storm. It's a process that demonstrates both the power of the Great Red Spot and the dynamic nature of Jupiter's atmospheric environment. The Great Red Spot's position relative to Jupiter's other atmospheric bands has remained remarkably stable over the centuries of observation. While the storm itself may vary in size and intensity, it stays locked within the same latitudinal band, suggesting that Jupiter's atmospheric circulation has maintained consistent large-scale patterns for centuries. This stability in position, combined with the storm's persistence, suggests that the Great Red Spot is not an accident or a temporary disturbance, but rather a fundamental feature of Jupiter's atmospheric dynamics. This positional stability is maintained by the jet streams that flow around Jupiter at different latitudes, creating a kind of atmospheric highway system that guides and constrains the movement of storms and other weather features. The Great Red Spot sits in a particular lane of this highway system, locked in place by the flow patterns that surround it. The temperature difference between the Great Red Spot and the surrounding atmosphere helps drive the storm's circulation, creating thermal gradients that contribute to the complex flow patterns within the system. The center of the storm is typically a few degrees warmer than its edges, creating convection currents that help maintain the storm's internal circulation and structure. These temperature differences might seem small, just a few degrees in an environment where temperatures are already hundreds of degrees below zero, but in the context of Jupiter's massive atmospheric system, even small temperature differences can drive enormous circulation patterns and maintain storm systems for extended periods. The storm's longevity raises intriguing questions about energy sources and atmospheric stability that challenge our understanding of how weather systems work. On Earth, storms dissipate relatively quickly because they lose energy through friction with the surface and encounter varying conditions as they move across different types of terrain. The Great Red Spot's persistence suggests that Jupiter's atmospheric dynamics operate under fundamentally different principles that allow for the maintenance of organized structures over timescales that would be impossible in terrestrial weather systems. This longevity has made the Great Red Spot a kind of natural experiment in atmospheric physics, allowing scientists to study how organized structures can persist in chaotic systems. The insights gained from this study have applications far beyond planetary science, contributing to our understanding of how complex systems maintain order and structure over long periods. Recent studies have shown that the Great Red Spot may be surrounded by a ring of smaller cyclonic storms that help isolate it from the broader atmospheric circulation. These smaller storms act like a protective barrier, helping to maintain the Great Red Spot's structure and preventing it from being torn apart by Jupiter's turbulent atmosphere. This discovery has revealed that the Great Red Spot is not a solitary feature, but rather the center of a complex system of interacting atmospheric elements. These surrounding storms create a kind of buffer zone around the Great Red Spot, shielding it from disturbances in the broader atmospheric circulation while allowing it to maintain its distinct identity. This protective mechanism may be one of the key factors that has allowed the storm to persist for such extraordinarily long periods. The storm exhibits what scientists call coherent vortex behavior, meaning that despite its enormous size and the chaotic nature of Jupiter's atmosphere, the Great Red Spot maintains its identity as a discrete, recognizable system. This coherence is remarkable given that atmospheric features on gas giant planets might be expected to quickly blend into the background turbulence, losing their distinctive characteristics and becoming indistinguishable from the surrounding atmospheric motion. This coherent behavior suggests that the Great Red Spot has internal feedback mechanisms that help maintain its structure and identity. These mechanisms operate like a kind of atmospheric immune system, correcting disturbances and maintaining the storm's essential characteristics, even as it interacts with the chaotic environment around it. The Great Red Spot occasionally appears to eat smaller atmospheric features that drift too close to its boundaries, demonstrating both its power and its ability to grow and maintain itself through interaction with its environment. These interactions can temporarily change the storm's appearance and provide insights into how material and energy are exchanged between different parts of Jupiter's atmosphere. When smaller storms are absorbed by the Great Red Spot, they don't simply disappear. Their material and energy become part of the larger system, contributing to its ongoing circulation and potentially affecting its color, size, or rotation rate. This process reveals that atmospheric features on Jupiter are not isolated phenomena, but rather parts of a complex, interconnected system where energy and material are constantly being exchanged. The storm's rotation creates what fluid dynamicists call a shear zone around its perimeter, where wind speeds change rapidly with distance from the storm's center. This shear zone helps to isolate the Great Red Spot from the surrounding atmosphere and contributes to its remarkable stability over time. The shear zone acts like a kind of atmospheric barrier, preventing the turbulent motions of the surrounding atmosphere from penetrating into the storm's interior and disrupting its organized circulation. Understanding these shear zones and how they maintain atmospheric boundaries is crucial for understanding not just the Great Red Spot but atmospheric dynamics in general. Similar shear zones exist in Earth's atmosphere and oceans, and studying the extreme example provided by the Great Red Spot helps scientists understand how such boundaries form and persist. Spectroscopic analysis of the Great Red Spot has revealed the presence of complex organic compounds, molecules containing carbon that form through photochemical reactions in Jupiter's upper atmosphere. While these aren't signs of life, they demonstrate the rich chemistry that occurs in the atmospheres of giant planets and provide insights into the types of chemical processes that might occur in similar environments throughout the universe. These organic compounds are created when simple molecules in Jupiter's atmosphere are broken apart by solar ultraviolet radiation and then recombine in new ways. The Great Red Spot's circulation brings these compounds up from deeper atmospheric layers where they're protected from radiation, exposing them to solar energy and creating the complex chemistry that may contribute to the storm's distinctive coloration. The Great Red Spot's appearance changes with viewing angle and illumination conditions, revealing information about its three-dimensional structure that wouldn't be apparent from any single perspective. When viewed from different perspectives by various spacecraft, it can appear more or less prominent, and these variations help scientists understand how the storm extends vertically through Jupiter's atmosphere and how its appearance relates to its internal structure. These viewing angle effects are particularly important for understanding the storm's vertical extent and structure. By combining observations from multiple spacecraft viewing the storm from different angles, scientists can create three-dimensional models that reveal details about the storm's internal organization and circulation patterns. The storm generates acoustic waves, MINDs, essentially sound waves, that propagate through Jupiter's atmosphere like cosmic music that we cannot hear. While these waves would be inaudible to human ears due to their low frequency and the medium through which they travel, they can be detected by sensitive instruments and provide information about the internal structure of Jupiter's atmosphere and the processes occurring within the Great Red Spot. These acoustic waves are created by the storm's circulation and the complex interactions between different parts of Jupiter's atmospheric system. By studying these waves, scientists can learn about conditions deep within Jupiter's atmosphere that cannot be directly observed, using sound as a probe to explore the planet's hidden interior. The Great Red Spot has served as a natural wind speed indicator for Jupiter's atmosphere, allowing scientists to map wind patterns and circulation systems across large portions of the planet's southern hemisphere. By tracking the movement of smaller features relative to the storm, scientists can determine how fast different parts of Jupiter's atmosphere are moving and how these motions change over time. This wind mapping has revealed that Jupiter's atmospheric circulation is incredibly complex, with multiple jet streams flowing at different speeds and directions. The Great Red Spot serves as a kind of atmospheric landmark, providing a reference point for measuring these complex flow patterns and understanding how they interact to create Jupiter's overall atmospheric dynamics. The storm's vertical extent appears to be limited by Jupiter's atmospheric structure, confined to the upper portions of the atmosphere where ammonia clouds form rather than extending down into the deeper water cloud layers or the presumed hydrogen-helium metallic core. This vertical confinement helps explain why the storm can maintain its structure over such long periods. It exists in a relatively stable atmospheric layer that doesn't experience the extreme conditions found deeper within Jupiter's interior. This layered structure of Jupiter's atmosphere creates distinct zones with different properties and behaviors, and the Great Red Spot appears to be primarily confined to the uppermost of these layers. This confinement may be one of the factors that contributes to the storm's stability and longevity. The Great Red Spot exhibits what's known as quasi-periodic oscillations, where certain aspects of its behavior, such as its size or rotation rate, vary in cycles that repeat over periods of months to years. Understanding these oscillations helps scientists predict how the storm might evolve in the future and provides insights into the complex feedback mechanisms that maintain its structure. These oscillations suggest that the Great Red Spot is not a static feature but rather a dynamic system that responds to changes in its environment while maintaining its overall identity. The periodic nature of these changes implies that there are underlying physical processes that operate on predictable timescales. The storm interacts with Jupiter's powerful magnetosphere in subtle ways that reveal the complex relationship between atmospheric and magnetic phenomena on gas giant planets. The movement of charged particles within and around the Great Red Spot can influence the local magnetic field, creating detectable signatures that help scientists study both the storm and Jupiter's magnetic environment. Jupiter's magnetosphere is one of the most powerful in the solar system, trapping charged particles and creating radiation belts that would be lethal to unprotected humans. The Great Red Spot's interaction with this magnetic environment adds another layer of complexity to its behavior and provides another tool for studying its internal structure and dynamics. The Great Red Spot has been observed to occasionally develop satellite storms, smaller rotating systems that orbit around the main storm like atmospheric moons. These satellite systems usually merge back into the main storm after a few rotations, but they provide insights into how the Great Red Spot interacts with its immediate environment and how smaller atmospheric features can be captured and incorporated into larger systems. These satellite storms are fascinating examples of how atmospheric features can interact and influence each other on Jupiter. They demonstrate that the Great Red Spot is not an isolated phenomenon but rather part of a complex atmospheric ecosystem where different features interact in complex and sometimes unpredictable ways. The storm's distinctive color may be partially due to its altitude, rising higher into Jupiter's atmosphere than the surrounding regions, and therefore being exposed to more intense solar ultraviolet radiation. This increased radiation exposure could drive the chemical reactions that create the storm's characteristic red hue, making its color a direct result of its elevated position in the atmospheric column. This altitude effect adds another dimension to understanding the Great Red Spot's appearance and behavior. The storm's elevation above the surrounding cloud deck not only makes it visually prominent, but also exposes it to different environmental conditions that affect its chemistry and evolution. The Great Red Spot has been used as a reference point for mapping Jupiter's coordinate system, serving as a kind of atmospheric prime meridian that allows astronomers to define longitude on Jupiter. Because it's such a prominent and persistent feature, astronomers use its position to define coordinates on Jupiter, much like we use the Greenwich meridian on Earth to establish our global coordinate system. This use of the Great Red Spot as a reference point demonstrates its importance not just as a scientific phenomenon, but as a practical tool for studying Jupiter. Its persistence and recognizability make it an ideal landmark for navigating Jupiter's complex and ever-changing atmospheric landscape. The storm exhibits complex internal circulation patterns that have only recently been revealed through high-resolution imaging from spacecraft like Juno and the Hubble Space Telescope. Rather than rotating as a solid body, different parts of the Great Red Spot move at different speeds, creating intricate flow patterns within the larger system that resemble the circulation patterns in Earth's oceans, but on a vastly larger scale. These internal circulation patterns are incredibly beautiful when revealed through time-lapse photography, showing swirling currents and eddies within the larger storm system. Understanding these patterns is crucial for comprehending how the storm maintains its structure and how energy and material are distributed within the system. The Great Red Spot's persistence has implications for our understanding of weather and climate on other gas giant planets throughout the universe. Similar long-lived storms have been observed on Saturn and Neptune, suggesting that such phenomena may be common features of giant planet atmospheres. This means that the Great Red Spot may not be unique to Jupiter, but rather an example of a type of atmospheric phenomenon that occurs throughout the cosmos. The study of the Great Red Spot, therefore, has implications that extend far beyond our solar system, providing insights that may help us understand atmospheric dynamics on the thousands of exoplanets that have been discovered orbiting other stars. Many of these exoplanets are gas giants similar to Jupiter, and understanding the Great Red Spot helps us predict what their atmospheres might be like. The storm appears to be gradually losing angular momentum, the rotational energy that helps maintain its structure. This loss of momentum may be one factor contributing to its observed shrinkage over the past century, though the exact mechanisms involved are still being studied. Understanding this momentum loss is crucial for predicting the storm's future evolution and ultimate fate. This gradual loss of energy raises questions about the storm's long-term stability and whether it might eventually dissipate entirely. While the Great Red Spot has persisted for centuries, it's not necessarily permanent, and understanding the processes that maintain or erode its structure is important for predicting its future. The Great Red Spot has been observed to influence the formation of other atmospheric features on Jupiter, demonstrating its role as a major player in the planet's atmospheric dynamics. The way it deflects and channels atmospheric flows can create conditions that promote or inhibit the development of storms in other parts of the planet, showing how atmospheric features on gas giants can influence each other across vast distances. This influence extends beyond just deflecting other storms. The Great Red Spot actually helps shape the broader circulation patterns of Jupiter's atmosphere, creating flow patterns that affect weather across much of the planet's southern hemisphere. The storm's internal temperature structure shows complex variations that reflect the three-dimensional nature of its circulation. While the center is generally warmer than the edges, there are also vertical temperature gradients and localized hot and cold spots that reveal the complex patterns of heat transport and energy distribution within the system. These temperature variations provide insights into how the storm maintains its circulation and how energy flows through the system. Understanding these thermal patterns is crucial for comprehending the physical processes that sustain the Great Red Spot over such long periods. The Great Red Spot occasionally exhibits what scientists call outburst events, where it suddenly becomes brighter or changes color for periods ranging from days to weeks. These events may be related to changes in the chemical composition of material being lifted from deeper atmospheric layers or variations in the intensity of the circulation that brings different types of material to the storm's visible surface. These outburst events are unpredictable and poorly understood, adding an element of mystery to the storm's behavior. They demonstrate that even after centuries of observation, the Great Red Spot continues to surprise scientists with new and unexpected behaviors. The storm has been observed to interact with Jupiter's radiation belts, near-regions of charged particles trapped by the planet's magnetic field. These interactions can create localized heating and may contribute to some of the chemical processes that give the Great Red Spot its distinctive appearance. The radiation environment around Jupiter is intense enough to damage spacecraft electronics, and the Great Red Spot's interaction with this environment adds another layer of complexity to its behavior. Understanding these radiation interactions is important for comprehending the full range of processes that affect the storm's evolution and appearance. The charged particle environment around Jupiter is unlike anything in Earth's vicinity, and studying how it affects atmospheric features like the Great Red Spot provides insights into physics under extreme conditions. The Great Red Spot's behavior provides insights into the physics of rotating fluid systems under extreme conditions, contributing to our understanding of fundamental physical processes that occur throughout the universe. The principles governing its motion and stability apply to many other systems in nature, from ocean currents to stellar atmospheres to the formation of galaxies. This makes the Great Red Spot important not just for planetary science but for physics in general. It's a natural laboratory where we can study fluid dynamics, thermodynamics, and electromagnetic interactions under conditions that cannot be replicated in any earthly laboratory. The storm exhibits what's known as beta drift, a slow migration in latitude caused by the variation in Jupiter's rotation rate with distance from the equator. However, the Great Red Spot's drift is much slower than would be expected from theory alone, suggesting that other factors help anchor it in place and maintain its position within Jupiter's atmospheric circulation system. This resistance to drift is another factor that contributes to the storm's remarkable stability. While theory suggests it should migrate more rapidly toward Jupiter's equator, observations show that it maintains its position with remarkable consistency, indicating that there are stabilizing mechanisms at work that we don't fully understand. The Great Red Spot has been observed to change its rotation speed in response to interactions with other atmospheric features, demonstrating its dynamic nature and its sensitivity to changes in its environment. These changes are usually temporary, with the storm returning to its baseline rotation rate after the interaction ends, showing that it has internal mechanisms for maintaining its characteristic behavior. These speed variations provide insights into how the storm responds to external influences and how it maintains its long-term stability, despite being constantly buffeted by other atmospheric features and disturbances. The storm's longevity may be partly due to Jupiter's lack of seasons, which provides a stable environment that doesn't subject the storm to the type of regular variations that might disrupt its structure. Unlike Earth, Jupiter's axis is tilted only about 3 degrees relative to its orbit, so it experiences minimal seasonal variations that might disrupt long-term atmospheric patterns. This seasonal stability means that the Great Red Spot exists in a relatively constant environment, without the regular changes in solar heating and atmospheric circulation that characterize seasonal planets like Earth and Mars. This stability may be one of the factors that has allowed the storm to persist for such extraordinarily long periods. The Great Red Spot generates turbulence that can be detected in the surrounding atmosphere for thousands of miles beyond its visible boundaries, creating a wake of atmospheric disturbance that extends far from the storm itself. This turbulence creates distinctive patterns in Jupiter's cloud formations that serve as indicators of the storm's influence and help scientists study how energy and momentum are transferred through atmospheric systems. This far-reaching influence demonstrates that the Great Red Spot is not an isolated phenomenon, but rather a major component of Jupiter's atmospheric system that affects conditions across vast regions of the planet. The storm has been used to study how atmospheric features on gas giant planets exchange energy and material with their environments, providing insights into fundamental processes that occur in planetary atmospheres throughout the universe. These exchange processes are fundamental to understanding how such planets maintain their atmospheric structure and composition over geological timescales. Understanding these exchange processes is crucial for comprehending how gas giant atmospheres evolve over time, and how they maintain their complex structures and circulation patterns over billions of years. The Great Red Spot's internal circulation includes both horizontal and vertical components, creating a complex three-dimensional flow pattern that helps maintain the storm's structure. Material spirals inward at some altitudes while spiraling outward at others, creating circulation cells that interact in complex ways to sustain the overall system. This three-dimensional circulation is one of the most remarkable aspects of the Great Red Spot, creating a structure that is far more complex than the simple rotating disk that it might appear to be when viewed from a distance. The storm occasionally displays what appear to be spoke-like features extending from its center toward its edges, revealing internal structure that may represent circulation cells within the larger system or could be related to the vertical transport of material between different atmospheric layers. These spoke-like features are visible only under the best observing conditions and with the highest resolution imaging, providing tantalizing glimpses of the storm's internal organization and the complex processes occurring within its boundaries. The Great Red Spot has been observed to influence the propagation of atmospheric waves across Jupiter's surface, creating disturbances that ripple outward through the planet's atmospheric circulation, like waves spreading from a stone dropped in a pond. These waves carry energy and momentum, helping to distribute the storm's influence far beyond its visible boundaries. Understanding how these waves propagate and interact with other atmospheric features is important for comprehending the broader dynamics of Jupiter's atmospheric system, and how different features influence each other across planetary scales. The storm's persistence through Jupiter's orbital variations demonstrates remarkable stability in the face of changing external conditions. As Jupiter moves closer to and farther from the Sun during its 12-year orbit, the amount of solar heating varies, yet the Great Red Spot maintains its basic structure despite these changes in the energy input to Jupiter's atmospheric system. This stability through orbital variations suggests that the storm is primarily driven by Jupiter's internal heat rather than solar heating, and that its structure is robust enough to withstand the relatively small changes in external energy input that occur as Jupiter orbits the Sun. The Great Red Spot exhibits what scientists call coherent structure, meaning that despite its enormous size and the turbulent environment in which it exists, it maintains recognizable patterns and behaviors that persist over long periods. This coherence is remarkable given the chaotic nature of turbulent fluid systems and demonstrates that the storm has found a stable configuration that resists disruption. This coherent structure is one of the most fascinating aspects of the Great Red Spot from a theoretical perspective, as it challenges our understanding of how organized structures can persist in chaotic systems. The storm has been used as a natural experiment in planetary-scale fluid dynamics, providing a unique opportunity to study atmospheric behavior under conditions that cannot be replicated in laboratory settings. By observing how it responds to various perturbations and changes in its environment, scientists can test theories about atmospheric behavior under extreme conditions. This makes the Great Red Spot invaluable for advancing our theoretical understanding of atmospheric dynamics and fluid mechanics in general. The Great Red Spot's interaction with Jupiter's jet streams creates complex wave patterns that can be detected across much of the planet's southern hemisphere, demonstrating how localized atmospheric features can influence planetary-scale circulation patterns. These waves carry energy and momentum, helping to distribute the storm's influence far beyond its visible boundaries. Understanding these wave interactions is crucial for comprehending how atmospheric features on gas giant planets influence each other and how energy is transported through planetary atmospheric systems. The storm appears to have a preferred size range. When it grows too large, it tends to shed material and shrink back toward a more stable configuration. This self-regulating behavior is one of the factors that may contribute to its long-term persistence, helping it maintain a stable size despite the various forces that might otherwise cause it to grow or shrink indefinitely. This size regulation demonstrates that the Great Red Spot has internal feedback mechanisms that help maintain its structure and characteristics within certain bounds, contributing to its remarkable stability over time. And so we come to the end of our gentle journey through the swirling mysteries of Jupiter's Great Red Spot, having explored 100 remarkable facts about this cosmic phenomenon that continues to fascinate and inspire us. From its ancient origins to its modern mysteries, from its enormous scale to its intricate internal structure, the Great Red Spot stands as one of the most remarkable features in our solar system. A storm that has outlasted civilizations, a tempest that has raged longer than humans have been studying the stars. As you drift towards sleep, perhaps carried by the rhythm of our exploration, let yourself imagine this great storm continuing its ancient dance in the depths of space. While you rest peacefully in your bed, while the Earth turns on its axis and carries you through the night, Jupiter's Great Red Spot continues its endless rotation, a cosmic clock marking time on a scale that dwarfs human experience. There's something profoundly comforting about the persistence of this storm, its faithful presence in Jupiter's atmosphere, serving as a reminder that some things in our universe endure beyond the brief span of human lifetimes. It has watched over Jupiter through countless rotations, through millions of Jovian days and nights, through the entire span of recorded human history and far beyond. The Great Red Spot reminds us that our universe is full of wonders that operate on scales both grander and more enduring than anything in our daily experience. It challenges us to expand our thinking, to consider the vast scales of space and time on which cosmic phenomena operate, and to appreciate the remarkable complexity and beauty that exists in the natural world. Thank you for joining me on this peaceful exploration through the atmospheric depths of our solar system's largest planet. Whether you absorbed every detail or found yourself drifting into dreams somewhere along the way, I hope you've discovered something that sparked your sense of wonder about the cosmos we inhabit. Wherever you are in the world right now, whatever time zone you're listening from, I'm grateful you chose to spend these moments exploring the universe with me. The fact that we can sit in the comfort of our homes and contemplate storms raging on distant worlds is itself a remarkable testament to human curiosity and ingenuity. Sleep well, and may your dreams be filled with the gentle rotation of cosmic storms and the quiet majesty of worlds beyond our own. Good night.